Let's take a look at chemical reactions and 4 categories of chemical reactions. Okay, now let's remember that a chemical reaction is a chemical change in property. So we are changing from one compound or element to a new substance, a new form of matter that has both physical and chemical properties different than its previous form of matter. Okay, so let's look at synthesis reactions. Okay, a synthesis reaction, I want you to remember that synthesis, think of to create, to build, or construct. So synthesis reactions often look like a template of A plus B yields AB. What we're doing in a synthesis reaction, we are taking 2 smaller forms of matter, maybe an element with a second element, and putting them together to form a new binary compound. Or we may be taking 2 small compounds and putting them together into a larger compound. Okay, so some examples for you. Simple one, hydrogen gas with oxygen gas to produce water. Okay. Now, often synthesis reactions look unbalanced. It looks like an oxygen disappeared here, but it didn't. The equation just needs to be balanced. So we can put a 2 there and a 2 there. And we'll have our balanced chemical equation. Okay, so synthesis, see, a single element reacts with another element to form a compound. Another example of a synthesis reaction might be water reacting with a gas, let's say SO3, sulfur trioxide gas, and when those 2 small compounds come together, they would form H2SO4, which we would call sulfuric acid. Okay. Again, here is your A, here is your B, and they come together, AB, to make a larger compound with new chemical and physical properties. Okay, so a synthesis reaction. A plus B yields AB. We're looking for 2 small pieces of matter coming together to form a larger piece of matter. Okay, much like constructing or building a puzzle. Now, let's look at decomposition reactions. Okay, decomposition, think of decomposing, decaying, breaking down, breaking apart. Okay, when we think of the word decomposing or decomposition, okay, so its template often appears as AB yields A plus B. One large form of matter breaks apart into 2 smaller forms of matter. Also notice it's the reversal of synthesis. Okay, it's the reversal. So we're undoing a synthesis. Okay, so let's say we had table salt sodium chloride. Okay, and if we were to decompose it, and with decomposition reactions, we often need electricity, some sort of energy, maybe some UV light energy source. We need some sort of energy to break these bonds to get the elements apart. Okay? And that would go back to its essential elements, the sodium and the chlorine gas. Now notice here with the chlorine, I put Cl2 as its elemental form because it's one of the few elements that exists as the diatomic molecule. And again, notice on a decomposition reaction, it often looks like the matter appears or disappears. The values, the numbers are different, but we just need to balance the equation so we get the appropriate ratios. So let's put a 2 here, and let's put a 2 here. So when we decompose 2 sodium chloride, we produce 2 sodium plus one chlorine molecule. Okay, so a decomposition reaction. And another example, compound many of you are familiar with is hydrogen peroxide. Okay, it's used on cuts and scrapes. You have a hydrogen peroxide, and you decompose it, and it decomposes readily in the presence of UV light, so sunlight. That's why it often is sold in brown colored bottles. When it decomposes, it goes down to water and oxygen gas. Okay. See the AB becoming A plus B. Now, it appears again that an extra oxygen is on the right side, but the equation is not balanced. After we write a reaction, we always go back and balance the equation. So let's put a 2 in front of the hydrogen peroxide. That'll give us 4 oxygens and 4 hydrogens. Then let's put a 2 in front of the water, and we'll have our 4 hydrogen, and now we'll have our 4 oxygen on the right side in the products as well. Okay, so synthesis and decomposition are reversals to one another. Okay. Alright, now let's take a look at the displacement reactions. Displacement reactions, we're pushing out, or we're replacing, we're displacing an element or ion is what we're doing here. So for a single displacement, often it'll have the template or the appearance of A being an element plus BC, and it yields AC plus B. Okay. We have a single element coming into a single compound and displacing it. Now, often this BC, this compound, will be an aqueous solution, and we will drop in an element, and then it will ionize and displace one of the elements. Okay, so let's try an example here. Say we have magnesium, and we react it with a copper chloride solution. Okay, we'll say copper 2 chloride solution. That is aqueous. So we drop the magnesium in, and the magnesium is solid. It's a solid metal, a light gray in color. We drop it in. This copper 2 chloride is an aqueous solution, so the copper and the chlorides are individual ions. The magnesium is more reactive than the copper metal, and so it will come in and it will push the copper out. It will cause the copper to precipitate, to become a solid, to return to its elemental state. And then the magnesium will go into solution as an ions and form an aqueous solution of magnesium chloride. Okay. So we have a single element coming in and pushing out another element. Now, why did the magnesium go after the copper and not the chloride? Well, magnesium forms a +2 ion. Copper isn't also a metal, and it forms a +2 ion, and the chloride ions are -1. So the magnesium, it being a positive ion, would be attracted to the negative ions and be looking to form a bond between them. Okay? So that's why the magnesium pushed out the copper, because it wasn't attracted to the copper by both of them being positive ions. The magnesium is attracted to the oppositely charged ions, the chloride ions. Okay? Let's try one more of these single displacement. Let's say we have zinc. Okay? And it is reacting with, let's say silver nitrate. Okay, silver nitrate solution, that's aqueous, and zinc is a solid. So again, the zinc would come into the solution and it would want to push out the silver, because zinc takes a +2 charge, it is a metal, Silver is a metal and takes a positive 1 charge. So again, see metal ion, positive ion, positive ion. They're going to be doing the displacement. One would be displaced. The nitrate is an NO3 with a negative 1 charge. So the zinc would be attracted to the nitrate. So we would have zinc, nitrate. We'd have a new solution event, and then the silver would precipitate out of solution and become a solid. Now, we need to balance this equation, so let's put a 2 in front of the silver nitrate so that we have the appropriate number of nitrogens and oxygens on both sides, and then let's put a 2 in front of the silver solid, and it's balanced. Okay? So our single displacement reactions. Now, finally, let's take a look at the double displacement. Okay? The double displacement are often called precipitation reactions because they oftentimes form an insoluble solid. Now, they may also form a gas or form water. That's likely as well. So, for example, a precipitation reaction, we might have, let's say we have potassium nitrate. These are often aqueous solutions, potassium nitrate, and it reacts with, let's say, how about a sodium sulfate. Now, with these reactions, we must look for precipitation, which is an insoluble solid. So in one of the earlier videos, we looked at the solubility table to predict whether or not a precipitate would form. So let's take a look at this one and see if a precipitate is likely to form. In the double displacement, because we have aqueous solutions, these are all ions, let's move the positive ions, the cations, to see what our potential products are. Our potential products could be the potassium with the sulfate, so K2SO4, and the sodium would go over with the nitrate potentially to form sodium nitrate. Now these are our potential products. But now if one of these is going to be a precipitate, it's going to have to be an insoluble solid. So we need to take each one of these and we need to use our solubility tables. Okay, these are found in your textbook. So let's look up these two compounds, the potassium sulfate and the sodium nitrate. Compounds containing sodium and nitrate are all soluble. So this would not precipitate. This would stay aqueous in solution. Now let's look up the potassium and the sulfate. Compounds containing potassium. They are also soluble. So both of these potential compounds are both soluble. When you do a double displacement reaction and both of your potential products are soluble, you have no precipitation occurring, so by that you have no reaction occurring. So this would actually not form any chemical changes or chemical reactions. Okay, let's try another one. Okay, so on these double displacements, we always want to reference our solubility tables to check, to ensure that in fact we will have precipitation or some sort of gas or water forming as a product. So let's try barium chloride. Let's have a solution of barium chloride, BaCl2 aqueous, and let's mix it with, well, let's use that sodium sulfate that we had. Okay, both of these are soluble solutions, aqueous solutions here. So our potential products would be the barium sulfate and a sodium chloride solution. Okay, that's our potential products. But first, before we even balance this equation, let's check our solubility tables to see if precipitation occurs. So we'll first look up the sodium chloride. We know it's table salt, so we know it will dissolve. It is soluble. Okay, chloride compounds are soluble. Ours contains sodium, none of these, so it is soluble. In fact, that will not precipitate. Now let's check for barium sulfate. So compounds containing sulfate are mostly soluble, but our compound contains barium. Yes, we have barium. Barium sulfate is insoluble. So this is a precipitate. It is a solid that would be forming. So we need to balance our equation since we do have a reaction occurring. So with double displacement reactions, we often look for precipitation to occur, the formation of a gas, or the formation of water. Okay, so these four, synthesis, decomposition, single and double displacement, are broad categories of compounds that we often study in chemistry.